Hello and welcome to the fourth of the lectures this week under this course titled Approximate Reasoning Using Fuzzy Set Theory, a course offered over the NPTEL platform. In the lectures so far this week, we have seen one particular generalization of fuzzy conjunction to that of what we call a triangular norm, or in brief T-norm. We have also seen some different types of continuities that we can impose on the set of T-norms. We have also seen some algebraic aspects both at the elemental level with respect to a T-norm and also at the level of a function. And using this, we have been able to give some kind of a classification of T-norms into some subclasses. In this lecture, we will look at three major types of constructions. Constructions where if you are given a single T-norm or a couple of T-norms, how to construct a T-norm from these, and also construction from, say, first principles. Through these constructions, we will also see that we can obtain very useful and insightful representations for some subclasses of T-norms. Well, let's take two algebras. As we have seen, an algebra is a set with one or more operations of possibly different arities, means they can be binary or n-ary operations. In this case, let's consider these two algebras where G is a set and star is a binary operation on G, and similarly G dash is a set and circle is a binary operation on G dash. And let's be given a one-to-one onto homomorphism between G and G dash. So one-to-one onto, we understand it's a bijection. That means, what is a homomorphism? Homomorphism is a structure preserving map. What does it mean? Phi satisfies this equality. Phi of x star y is equal to phi x circle phi y. Now, in plain English, what does it mean? Take two elements x and y from G. What this says is, it does not matter whether you first take x and y and operate with star, which is the operation on G, and then apply phi on it, take the image of this x star y and go to the codomain, or first itself go to the codomain through phi, that means given x and y, go to G dash as phi x phi y and do the operation there, which is circle in G dash. Both these should actually be identical. So this is what it means to say the structure, the algebraic structure is preserved by this map, and that is what we call a homomorphism. Notice one thing, that since phi is one-to-one onto, which is bijection, it is invertible, and hence we could actually obtain the operation star as follows. X star y is phi inverse of phi x circle phi y. Note that initially we began with two algebras, G star and G dash circle, and a homomorphism. Now, what we see is, if you are given G and G dash and an operation circle on G dash, which makes it a particular algebra, and if we know that phi from G to G dash is homomorphism, one-to-one onto homomorphism, that means it preserves the structure, whatever structure that circle imposes on G dash, if it's preserving it, then the star operation on G actually can be obtained as the above formula. Let's see whether we can put this to good use in the context of T-norms. If we take the set 0, 1, we know that any T-norm makes it a commutative integral monad. So let's consider two T-norms, T star and T. For the moment, let's assume that both are known to us. So we actually have two commutative integral monads, just like how we started with two algebras G and G dash earlier. Now what we need is a structure preserving map. That means we need a map from phi from 0, 1 to 0, 1. How should it look like to be able to preserve the structure? It can be shown it is enough if it is an increasing bijection. So that means one-to-one onto increasing, which clearly means it is strictly increasing. What is interesting is, since now we know the underlying set G, which is 0, 1, we can show that any increasing bijection phi on 0, 1 to 0, 1 should also be continuous, such that phi of 0 is 0 and phi of 1 is 1. Now, let's consider the set of all such increasing bijections. Now, given any one bijection from the set under T norm T, we can actually construct T star, just like how we saw earlier. In this sense, we will denote this T star by T phi, because it tells us that it comes from a particular phi and also particular T norm. So these are the two things that are fixed. Given a T norm and an increasing bijection on the unit interval 0, 1, we see that we can construct a T norm T phi. How do we construct it? T phi of xy is equal to phi inverse of T of phi x phi y. This is essentially exactly the same as the formula that we had before, where if star were not known, it can be obtained like this. Now we are coming up with a new T norm T star, which we will denote henceforth as T phi, so that through the symbolism we will make it clear what is the T that we are referring to and what is the phi that we are referring to. And it can easily be seen that such T norms that we obtain, T phi, they are in fact T norms themselves. That means they will be commutative, associative, the identity will still be 1 because phi of 1 is 1, and it will also be monotonic because phi is an increasing bijection. Let's look at what are the properties this transformation preserves. If originally T were continuous, T phi will be continuous. If T is Archimedean, please recall, that means if you take any two elements x and y from 0, 1 interval, and if you operate, there will exist an n such that if you operate x on itself n times, it will become smaller than y. Similarly, there will exist an m such that if you take this y and operate y on itself with respect to this T norm T m times, it will become smaller than x with respect to the usual ordering on 0, 1. So this is what we mean by if this happens for every pair of elements, we say that the T is Archimedean. Now, if T is originally Archimedean, then this T phi is also Archimedean. If T is strict, that means it is continuous and strictly monotone, then T phi is also strict, continuous and strictly monotone. If T is nilpotent, T phi is also nilpotent. What is nilpotence? Nilpotence as such means if you take an element x, then there exists an n such that if you operate x on itself with respect to the T n times, it actually becomes 0. And a nilpotent T norm means that every element from open 0, 1 is actually a nilpotent element with respect to the T. So now these are the properties that this transformation actually preserves. Often in the literature you will see this as T phi is referred to as phi-conjugate of T. That's a nomenclature that is very common and popular. So we will also use this often. Let's look at some examples. Let's take the Łukasiewicz T norm, and for the increasing bijection, let's look at x square. Clearly, phi inverse x is root x. Now, if you actually work out what it will turn out to be, so we have TLK of xy is this, maximum of 0, x plus y minus 1. We have phi of x to be x square. So phi inverse x will be root x. Now what we want is TLK of phi of x square. This is phi inverse of T of TLK of phi x phi y. So this will be phi inverse of TLK of phi x phi y is maximum of 0, phi x we can substitute as x square plus y square minus 1. Phi inverse is square root of this, so it is essentially square root of maximum of 0. So this is what you will get as the phi conjugate of TLK. Now how will it look like, the graph of it? We know this is the usual Łukasiewicz T norm. The modified, the phi conjugate of Łukasiewicz T norm with respect to x square looks like this. You will see that all the properties are valid If it is nilpotent, it will continue to be nilpotent. If it is Archimedean, it will be Archimedean. It is also continuous. Now let's look at Tp of xy. And let's for the moment consider phi x to be xy, which means phi inverse x is root x again. Now if you want to find out what is Tp phi of xy, this should be phi inverse of Tp of phi x phi y. This is phi inverse of phi of x into phi y. This is phi inverse of phi x is x square, y square. Now phi inverse is root of this x square, y square. And what we get is actually xy, which is Tp. So you see here, there are some bijections which actually do not, their conjugate turns out to be the original T-norm itself. And you can easily see that this will happen for any x power m when n comes from n. So let's consider a different bijection. So let's consider this bijection phi of x, which is 2x square minus x power 4. Clearly this is increasing. At 0 it is 0, at 1 it is 1. If you look at what is the inverse of this, without much difficulty you can get this root 1 minus root 1 minus x. This is the product T-norm, and if you are wondering how these two bijections would look like, this is how they would look like. The blue curve is the original phi, 2x square minus x power 4. The red curve is the phi inverse. Note that both of them are increasing, as you can immediately visualize. Now what is the phi conjugate of product T-norm with respect to this phi? Well, it looks like this, a little scary formula, but it's not very difficult to get because you know how phi inverse looks like. So on the left you see actual product T-norm. Now let's graph the phi conjugate of this product T-norm. This is how it looks like. So visually there is not much of a difference, but you will see that both of them are Archimedean, both of them are continuous, and they are strictly monotone. But however, of course, they are not identical. So for the product T-norm, there are bijections which will give you different T-norms when you apply the phi conjugate on the product T-norm. Well, let's look at obtaining some representations through this. What do you mean by representation? So knowing the properties of a T-norm, can you say how it would look like? Is there a clear formula that we can give for it? Firstly, if you have a T-norm T such that for every bijection that you can think of, increasing bijection on 0 1 that you can think of, if the phi conjugate of that T happens to be T itself, like in the case of product T-norm, we took phi to be x square and we found that the phi conjugate of Tp was actually Tp. But for a different phi, it was not so. However, if for a T-norm, no matter which increasing bijection on the unit interval you consider, if T phi is equal to T, then what we know is it either has to be the minimum T-norm or the drastic T-norm. So you see here, we have some kind of an idea of what characterizes the minimum or a drastic T-norm. But this does not give us any more information. Of course, both minimum and drastic themselves, they're actually very easy to represent also in terms of the formula. They're simple, they're not very difficult. But this tells you if you have a T-norm, no matter what phi you apply on it, it remains the same, then you know that it has to be either the minimum or the drastic T-norm. Now, what about strict T-norms? It is interesting to note that we can show that if T is a strict T-norm, then T is actually a phi conjugate of the product T-norm. Now here is where we can look at this any strict T-norm in terms of this phi conjugacy of a product T-norm. Now, it is not enough to know this, we in fact even know the formula, how it would look like. That means any strict T-norm T would look like this, phi inverse of phi x dot phi y. So the moment you come up with a phi and substitute in this formula, you know it has to be a strict T-norm. Not only that, if you take any strict T-norm, that means a continuous and strictly monotone T-norm, you know that it will look like this, and All you need to do is find that particular phi for which you can give this representation. Now this is with respect to strict t-norm. What about nilpotent t? What are nilpotent t-norms? Continuous, and every element is a nilpotent element. And what's a nilpotent element? There exists an n such that xt of n is 0. Now, T is a nilpotent t-norm if and only if T is a phi-conjugate of the Lukasiewicz t-norm. Once again, what it means is, if you take any nilpotent t-norm, it is sufficient to think of it as some phi-conjugate of the Lukasiewicz t-norm. So that means any nilpotent t-norm, the moment you think of it, you are only searching for an increasing bijection on 0, 1 such that it can be easily constructed. Now, when we introduced the product t-norm and the Lukasiewicz t-norm, we saw that they were not giving us fantastic algebras or what we expected, as in the case of classical set theory. However, you see here, when we are dealing in the space of triangular norms, they actually hold a very unique position. Let's continue. Well, in the previous case, given a t-norm, we picked up an increasing bijection on 0, 1 and modified that given t-norm into a new t-norm. Now let us start with just a function from 0, 1 to 0, infinity, which is a continuous bijection. And consider this function tf. The f there denotes that this t has been constructed from the function f. Let's define this tf of xy as f inverse of f of x plus f of y. Now the question is, can tf be made a t-norm? Now it is immediately clear that this tf is commutative. Is it also associative? It is easy to see it is the case. Look at this. We are defining it as f inverse of f of x plus f of y. Now, associativity means what we want is this should be equal to tf of let's consider this part LHS. By definition, this will look like f inverse of f of x plus tf of yz. Now this is nothing but f inverse of f of x plus f inverse of should have been f of t of x, right? F circle f inverse of f of y plus f of z. Now f and f inverse, they are inverse of each other. You can cancel this, and what we are left with is f of x plus f of y plus f of z. And from the way we have expanded, it is clear that if you expand the right hand side, that will also be turned out to exactly the same form. That means we have a function which is both commutative and associative. Now let's ask the question, is tf of 1x equal to x? Tf of 1x equal to x means we are asking this question. It means f inverse of f of 1 plus f of x should be equal to x. And since we know that f is bijective, this implies f of 1 plus f of x is actually equal to f of x for any x in 0. Now, since these are real valued number functions, so these are real numbers, what we get is f of 1 has to be 0. So if you want 1 to act as an identity, then we want that the function f at 1 it should take the value 0. But now look at it, this also means something else. You can look at this function like this. It's essentially a map from 0, 1 to 0, infinity. We are making 1 go to 0 and we want it to be a bijection, which means 0 has to go to infinity. So this means f of 0 has to be an infinity. The only thing that is left is it should be monotonic. When can we make tf to be monotonic? It is clear that f has to be strictly decreasing, because 1 goes to 0 and 0 goes to infinity. That means with respect to the usual order on 0, 1, we see it's a decreasing function. So if we have all these things, we have monotonicity, identity, commutativity and associativity, which means we can get a T-norm. So we start with the function f, which is continuous, strictly decreasing. F of 1 is 0 and f of 0 is infinity. And we define the function tf like this. Now notice one thing. Compared to the previous construction, how does it differ, or what are the similarities? Here we start with the function f and the operation plus. So here g, we can look at it as just the 0, 1 interval. G dash circle is essentially the commutative monoid that we have on R plus, the set of non-negative real numbers with addition. It becomes a commutative monoid. 0 is the identity there. And now we have f to be a continuous bijection. And so in this sense, it is comparable to the previous construction that we had. Of course, there we start with a T-norm, but instead here we are starting with a commutative monoid on a different domain. Let's look at some examples. Is there really a function f from 0, 1 to 0, infinity, which is a bijection? Well, look at this function minus ln x. We know that immediately f inverse of x is e power minus x. And if you apply this formula, tf of xy is f inverse f of x plus f of y. This is what we get. Tf of xy is this, which on simplification looks like this. And we know that e power ln, they are inverse of each other, which means we get x dot y, which is essentially the product T-norm. So that means through this construction also, for a particular f, we are able to get product T-norm. And remember, recall that any strict T-norm is actually phi conjugate of Tp. So immediately you should see some connections, but going forward it will become amply clear. Now the question is, what if f is not a bijection? That means f of 0 is less than infinity. What do we do? Because we don't have a bijection, we don't have an inverse. How do we handle this case? We look at what is called a pseudo inverse of f. Now this is not a very difficult concept. You see here, before, for a bijection we had the entire 0, 1 being mapped onto the 0, infinity interval. But now what we have is 0, 1, 0, infinity. 1 is being mapped to 0, but f of 0 perhaps is some value which is less than infinity. Now how do we define the pseudo inverse? For anybody here between 0 and f0, you can always find an inverse. But anybody above f of 0 to infinity, what we do is we map them to again 0. So this is how we define the pseudo inverse of f. So if x belongs to 0 f, the interval 0 f0, then it is the usual inverse. If it is greater than f of 0, then we map it to 0. So now consider an f which is continuous, strictly decreasing. F of 1 is 0 and f of 0 is less than infinity. And use the same definition of tf, except that instead of inverse, let's use the pseudo inverse. Now once again it can be shown that this turns out to be a T-norm. Let's look at an example first. Let's consider f of x is equal to 1 minus x. That means the function you have looks like this. 1 minus x, f of 1 goes to 0, f of 0 actually goes to 1. So you see that this is not a bijection from 0, 1 to 0, infinity. What is the pseudo inverse? It looks like this, which is again clear, because between 0 to 1, we are using the usual inverse. Between 1 and infinity, we use the value 0. Now let's construct the tf from this function. So this fx, this f inverse x, f pseudo inverse x. And how do we construct? As f pseudo inverse of fx plus fy. Now in this case, f of x is 1 minus x. So let's substitute that 1 minus x plus 1 minus y. This turns out to be 2 minus x minus y, which is clear. Now comes the question of applying the pseudo inverse. What do we know? we will apply 1 minus x, the actual inverse, only if the argument lies between 0 and 1. That means we want that 2 minus x minus y should be less than or equal to 1, between 0 and 1. So that means we have two cases to consider. If 2 minus x minus y is less than or equal to 1, then it is 1 minus that argument, in which case it is 1 minus 2 minus x minus y. If 2 minus x minus y is greater than 1, strictly greater than 1, then it is 0. Now let's simplify both the equations on under the cases and also that we get as the value. This is simply x plus y minus 1, and this, if you take minus x minus y that side and 1 this side, all you see is that x plus y is greater than or equal to 1. And similarly, this is the case where x plus y is strictly less than 1, but in this case you will see that they actually coincide, so it's not a problem even if you use an inequality. But what is this? You could also write it like this: max of 0 comma x plus y minus 1, which is essentially your Lukasiewicz T-norm. So you see here, even through this construction, you are able to get both product and the Lukasiewicz T-norm. Now, through this construction, do we get some interesting representations for some subclasses of T-norms? Look at this. What we have is an f from 0 1 to 0 infinity, which is continuous, strictly decreasing, with f of 1 is 0. Now we do not talk about whether f of 0 is infinity or less than infinity. Let's only talk about what happens to f at 1. And consider this particular construction using the pseudo inverse of f. Any such function f, we call it a continuous additive generator of the function tf. And we know that this actually is a T-norm. Tf is a T-norm. So we say it's a continuous additive generator for a T-norm, which we denote by tf. What is interesting is, if you consider the class of continuous Archimedean T-norms, that means it's both continuous and also Archimedean. Note, Archimedean means for any pair of elements, there exists an m such that x bar m with respect to t is less than y. Similarly, there will be an m such that x bar m with respect to t is smaller than y. There exists an m such that y bar m with respect to t is smaller than x. Now, what is interesting is this. If you take any continuous Archimedean T-norm, you can see that there will exist a continuous additive generator f such that this t is obtained from it. Remember, when we thought of a strict T-norm, we always were searching for an increasing bijection on 0 1 to 0 1 such that we could just use that and then get the T-norm as a phi conjugate of product. Similarly, if you know it is a nilpotent T-norm, look for a phi and get the T-norm as a phi conjugate of the Lukasiewicz T-norm. Now what we are saying is, if you consider any continuous Archimedean T-norm, all you need to do is look for that corresponding continuous additive generator. Once you find that f, immediately you can find the t. Or if you want to think of a continuous Archimedean T-norm, you can always think of it as having a continuous additive generator, and this is exactly the formula that it will have with respect to that f. That's the power of representation results. It doesn't stop there. What about strict T-norms? Because we know that strict T-norms are also continuous and Archimedean, just that they are also strictly monotone. What we can say is T is a strict T-norm if and only if T is generated by a continuous additive generator and the generator is such that f of 0 is infinity, just like minus ln x. And you must now immediately be in a position to guess that nilpotent T-norms can also have a similar representation. Yes, they do have. Any nilpotent T-norm can be thought of as being generated from a continuous additive generator f such that f of 0 is less than infinity. Means f of 0 is finite. Well, let's look at the two constructions that we have seen so far and the representations that they have given us. From bijective transformations, what have we got? That any strict T-norm can be looked at as isomorphic or phi conjugate of product, and similarly nilpotent T-norm is isomorphic to the Lukasiewicz T-norm. From additive generators, what we got was that any continuous T-norm can be thought of as being generated by an f, and in the same way, if it is strict or nilpotent, it is still generated by a function f. It all depends on whether f of 0 is infinity or finite. Now, if you consider the class of T-norms themselves, you can have a subclass which is the class of continuous t-norms, also the class of Archimedean t-norms. The question is, do they intersect? Yes, we have some examples, specifically that of Vukashevich and the product t-norm. Now, is there a t-norm which is continuous but not Archimedean? Yes, the minimum t-norm. Note that we have it is an idempotent t-norm. The moment you have an idempotent element, it will not, how many ever times you operate, it will not go below itself. It will just resolutely stand there. Is there a t-norm which is Archimedean but not continuous? Yes, the drastic t-norm. Is there a t-norm which is neither continuous nor Archimedean? Yes, the nilpotent minimum. Because it is not continuous and it has an idempotent element, which means it's not Archimedean. So you see here, the choice of example that we have taken, 5 examples that we have taken, they actually capture different parts of the space of t-norms. But this diagram was not only to illustrate that. This diagram is to ask a question. Now we know that we have a characterization for continuous Archimedean t-norms. That means essentially either they are strict or nilpotent in this form. This is what we have known now. That is, if it is continuous Archimedean, then we know that it has such a representation. The question now is, what if it is only Archimedean? Can we give a representation? Well, that is not known, but however, it can be said that if you have an additive generator, whether continuous or not, it will turn out to be Archimedean. Now let's ask the same question for the set of all continuous t-norms. Can we have a representation for this? Well, hopefully soon. That's what takes us to the third type of construction. What do we have here? So let's take the unit interval, and you see the diagonal plotted there. Let's for the moment take 2 intervals, A1, B1, A2, B2, and we are given 2 t-norms, T1 and T2. So in this case, A1, B1 is just 0.2, 0.4 and A2, B2 is 0.6, 0.8 on the figure. So note that these are open intervals. And we are given 2 t-norms, T1 and T2. What do we want to do with this? We want to now construct the square, A1, B1 square and A2, B2 square. And what we want to do is, we want to restrict T1 and T2 only to these 2 squares. That means only when the values come from these 2 squares, from A1, B1 square, T1 will act on it. And if it comes from A2, B2 square, T2 will act on it. So essentially what we want is a way of reducing T1, which is originally defined on 0, 1 square, unit square, to just this A1, B1 square. And what we want this, let's denote this restricted T1 as T1 theta. So we want it only on this term, restricted term. How do we do this? Well, from what we have seen so far, it appears that we could just make use of a transformation. A phi from A1, B1 to 0, 1. One such phi is just the usual linear transformation. Using this, we could define T1 tilde of xy like this. Remember, T1 tilde x and y are coming from A1, B1. Now, we want to apply T1, but T1 acts only on 0, 1 square. But that's what phi does. Phi takes x, which is in A1, B1, to 0, 1. Similarly, phi of y is also in 0, 1. And this is how it is defined. Now, if you look at it, this is just a linearly transformed form of arguments, and T1 is acting on them. And what is interesting about this T1? If x is A1, then this is 0, so then this is 0. If both x and y are B1, then this is T of T1 of 1, 1. That means at this point, B1, B1, this value is 1. So within this, it still looks like it is being mapped between 0 and 1, which is what T1 will do. Now, what we want is, we want to construct a T-norm on the entire domain 0, 1 square using these 2. How do we do this? We do it like this. Look at this. If you are given many such T-norms, in this case it was just only T1, T2, many such T-norms, let's look at this as T1. So that means, whenever x and y come from A1, B1 square, this is how T of xy will be defined. A1 plus B1 minus A1, T1 of this value. Now once again at A1 what happens? At A1, when one of them is A1, that means we are looking at either this boundary or this boundary. If this is A1, then this is 0, so this entire thing is 0, bk minus ak into that is 0, it's only A1. So at this point, or on this entire interval, it will be just A1. Now what happens at this point? When both x and y are B1, that means this is 1, A1 plus B1 minus A1, which is B1, so at this point it is B1. So here it is A1, and here it is B1. So based on this, what we do is, we can actually, for the rest of the domain, we can allocate it to the minimum T-norm. Now, it can be verified that this is a T-norm, means commutative, associative, increasing in both variables, and one will still remain as the identity element. So such a construction is called the ordinal sum construction of T-norms. And in this case, for this particular figure, we would be writing it like this. So you see here, we denote that there are two T-norms and accordingly two intervals. A1, B1 is 0.2, 0.4, A2, B2 is 0.6, 0.8, and in the rest of the places it is the minimum T-norm. So that is how we understand. Now it is a case for two T-norms, but we could have many, countably many T-norms, Ti, and this is what we will get. This is how we represent it. Let's look at some examples. So each of the T-norms that we take in this ordinal sum, we call it an ordinal summand. So in this case, we have only one summand. That means from 0.2 to 0.4, we are using the Lukasiewicz T-norm to accordingly scale the domain and use the function TLK to obtain the values for the T-norm. So as you see here, everywhere else it is minimum, only here it is getting the values as some transformed values from the Lukasiewicz T-norm. Instead, if you use the product T-norm, you will see that essentially we are taking the Lukasiewicz T-norm and embedding it, some scaled version of it. Similarly, a scaled version of TP is embedded over this domain 0.2, 0.4 square. So now you see here, there are two summands. Between 0.2 and 0.4 it is Lukasiewicz, 0.6 and 0.8 it is product, and you see this. Note that we are modifying the minimum with two continuous T-norms, Lukasiewicz and product, and still it remains to be continuous. Now this is two summands. It is not mandatory that both these summands, the T-norms that you use are different. They can be same. This is one example of it. It is also not mandatory that we should only use continuous T-norms to construct this. So Lukasiewicz is continuous, and as you can see, the drastic T-norm is not. Now, we ask the question, can we have a representation for any continuous T-norm? So we know that we have for this part, we want it for the entire red square. Now, what are the continuous T-norms that we know of? This prototypical examples. Lukasiewicz, continuous and nilpotent. Product, continuous and strictly monotone. Minimum, which is continuous but not Archimedean. What is interesting is, it can be shown that any continuous T-norm is in fact an ordinal sum of continuous Archimedean T-norms. Now remember, continuous Archimedean T-norms. The continuous Archimedean T-norms themselves are representable T-norms. That means they can be obtained from continuous additive generators, and they can either be strict or nilpotent, which means either they are isomorphic or phi-conjugate of TP or TLK. And outside of that, you have only minimum. So which means these are the three T-norms that are playing a role in constructing continuous T-norms. In fact, it can be written like this. T is a continuous T-norm if and only if T is an ordinal sum of some T-norms, and each Ti looks like this. Each Ti is either minimum, Lukasiewicz, or product. So with this, we have found for a large subclass of T-norms, a representation for them, either in terms of phi-conjugacy or in terms of continuous additive generator or in terms of the ordinal sum representation. So far we have seen three constructions. Each one of them have led to a representation for a particular subclass of T-norms. From bijective transformations, we saw that any strict T-norm is phi-conjugate of product. Similarly, any nilpotent T-norm is a phi-conjugate of Lukasiewicz. From additive generators, we found that every continuous Archimedean T-norm is generated by a continuous additive generator. And from ordinal sum, we saw that any continuous T-norm is an ordinal sum of T-norms, each of which is either minimum, Lukasiewicz, or a product T-norm. Now, what next? In the next lecture, we will look at complementation, and through complementation, the dual function of a T-norm. We have seen complementation from a lattice theory point of view. It is similar to that what we will take the beginning approach, but of course later on we will diversify. This is what we will discuss in the last of these lectures this week. And for this lecture, the topics that are covered in this lecture, this book by Kleeman, Messier and Park, titled Triangular Norms, is a very good resource for you. Thank you once again for joining me in this lecture, and hope to see you soon in the next lecture. Thank you.